Hi, I'm Xiao from the National University of Singapore. I would like to present our work, Contrastive Variational Reinforcement Learning for Complex Observations. Deep reinforcement learning has achieved great success in many tasks, especially in games. For example, it has outperformed human players on classic Atari games and the game of Go. However, these tasks has a relatively simple observation space, and applying RL to real-world scenarios is still difficult. Imagine driving a car through the crowd in this case. Can our existing RL algorithms do this? The answer is probably no. The task is to discover the drivable area and determine the next action. But the observations that the robot receives contains the changing appearance of the nearby pedestrians, the contents of the billboards, and etc. So this irrelevant information introduces an extremely low signal-to-noise ratio and make the RL difficult. In this paper, we want to answer this question, how to achieve sample-efficient and robust model-based reinforcement learning against complex observations. Standard model-based RL makes decisions by reasoning a word model which describes the dynamics of the environment. Given pixel-level input, the word model is often parameterized by variational autoencoders. It maximizes its observation likelihood with pixel-level reconstruction. However, reconstructing the observations from a state directly has to model the entire observation space, including irrelevant background information. And as a result, this gives a much more difficult optimization landscape and make the RL hard. In this paper, we introduce CVRL, Contrastive Variational Reinforcement Learning for Complex Observations. CVRL motivates the representation learning from the mutual information perspective. Instead of pixel-level reconstruction, we maximize the correspondence of the correct state and observation pair while minimizing the correspondence of the state and a set of irrelevant observations. In the driving example, we can choose the contents of the billboards as negative samples and minimize the focus of the network on the irrelevant information while maximize the focus on the useful information. And as a result, this is much more robust compared to reconstruction. To effectively and efficiently optimize the model, we introduce a contrastive evidence lower bound, which mathematically lower bounds the standard generative evidence lower bound used in the VAEs. We avoid modeling the observations directly and replace the reconstruction by contrastive learning, and for the reward, which is simple to model, we directly predict it. CVRL chooses the action by reasoning the learned dynamic model with model predictive control, guided by a learned heuristic, which is an efficiently and effectively trained actor-critic model. So this allows CVRL to reason for long horizon behaviors robustly. We evaluate CVRL on a set of challenging Mujoco control tasks defined in the DeepMind control suite. Specifically, to simulate the complex background, we introduce natural Mujoco, where we replace the original simple background with a set of natural videos sampled from the IL-SVRC dataset, which is collected in the real-world scenarios. So natural Mujoco is more challenging because of the complex backgrounds compared to the standard Mujoco tasks. We compare CVRL with a model-free SAC baseline and the state-of-the-art generative model-based RL method, Dreamer. We observe that CVRL outperforms the SAC and achieves a comparable performance with Dreamer on the standard Mujoco tasks. In addition, on natural Mujoco tasks with complex backgrounds, CVRL significantly outperforms the generative Dreamer and SAC. Specifically, we emphasize that on 8 out of 10 cases, CVRL achieves comparable performance with or without complex backgrounds, while the generative Dreamer has experienced a dramatic performance drop in all cases. This indicates that contrastive learning effectively captures the dynamics of the environment even with complex observations. We also evaluate CVRL on box-pushing tasks with simulated robot, where the challenge is the dynamic shadow casted by the robot arm and self-occlusion. We noticed that CVRL has learned faster compared to the other two baselines and achieves a higher reward with a shorter execution length. These are the visualizations of our experiment, where we can see that CVRL successfully handled all tasks. Okay, so our codes are publicly available. You can visit our GitHub page and visit the project page for more information. Thank you.